Hello everyone, here are videos for civil engineering. Welcome to the channel Amazing Civil Engineering Studies. Here we have different videos on all topic of civil engineering. Please subscribe and press bell icon, like and share as many as possible.
In this video we will come to know about cement, its manufacturing, properties, tests performed on lab as well as site, types of cement, and uses. Cement is a binding material which makes a bond between aggregates and reinforcing materials together. It is a mixture of different compounds consisting mainly of silicates and aluminates of calcium formed out of silica, calcium oxide, aluminum oxide, and iron oxide. It works as same as glue we use for sticking two objects together, but it can bind natural compounds like sand and aggregate. When water is added to cement, the hydration process starts. Hydration is the chemical process between water and cement, and which produce a bond between sand and aggregate. Importance in construction. It is widely used binding material in the construction industry. After its invention, cement became popular among all other building materials. It almost absolute the use of other binding material like clay and lime. We can say that cement is ruling construction form past hundreds of years. It is a major element in concrete and it can hold the structure together for a long time. Why cement is popular building material? Its use is the same form all around the world. It can bind other construction material together. It is vast application in the construction industry like, for plastering, tiling, finishing, interior, and exterior work finish, etc. It is made today modern world possible. Raw materials of Portland cement. Raw materials: calcareous rocks material, Caco 375% such as limestone, marl, chalk. Argillaceous rocks material, Caco 3. Argillocalcareous rocks material, 40-75% Caco 3 such as clayey limestone, clayey marl. Portland cement can be manufactured from any two groups above. This raw material must be used in proper form and proportions of lime, silica, and alumina. Cement manufacturing process. What is cement made of? Cement manufacturing process and what is cement made of? It can be discussed conveniently under two headings: selection of raw materials and manufacturing methods. Raw materials of cement. Most important raw materials. What is cement made of? Required in the manufacture of Portland cement are limestone, clay, gypsum, fuel, and water, in wet method. 1. Limestone. These are sedimentary, calcium carbonate rocks, Cac 03. Most commonly they contain a small amount of magnesium carbonate also. Besides, usual impurities in limestone are those of iron oxides, silica, and alkali. All limestone, therefore, are not suitable for the manufacture of cement. It is essential that limestone selected for manufacture of cement should not contain magnesium carbonate, more than 5%. Free silica, even in small proportion. Iron sulfides, more than 3%. 2 clay rocks. These are also sedimentary rocks made up mostly of hydrated silicates of aluminum. Like limestone, they also contain some impurities as iron oxides, free silica, alkali, and magnesia. It is essential that those clays which are to be used for manufacturing of cement do not contain these impurities beyond the permissible limits. Some limestone are rich in the clayey matter to the extent of 30%. They are called cement rocks because they can be used as a single raw material for the cement manufacturing process. 3. Gypsum. It is generally added in very small amounts, about 2% by weight, to the burnt cement, called clinker, after it is taken out from the kiln and before it is sent for grinding. Gypsum is a sedimentary rock having a composition of calcium sulfate, CaSO. 4. 2H. 2. O. It is added for imparting a retarding effect in the setting of cement. Without gypsum the cement would set, within minutes after adding water into it. It will be, therefore, very difficult to work with such a type of cement. Addition of gypsum at the manufacturing time, however, increases the initial time to desirable limits. Methods of manufacturing process of cement. Cement is manufactured through a closely controlled chemical combination of calcium, silicon, aluminum, iron, and other ingredients. Common materials said to manufacture cement include limestone, shells, and chalk or marl combined with shale, clay, slate, blast furnace slag, silica sand, and iron ore. These ingredients, when heated at high temperatures, form a rock-like substance that is ground into the fine powder that we commonly think of as cement. At present, Portland cement is manufactured by 2 processes, dry process and wet process. The main difference between these 2 methods of manufacturing of cement is that in dry process, calcareous and argillaceous raw materials are fed into the burning kilns in a perfectly dry state. In the wet process, however, these materials are supplied into the kiln in the form of an intimate mixture with water called slurry. Dry process of manufacture of cement. Following are the main steps in this process of cement manufacturing. Treatment of raw materials. Burning of the dry mix. Grinding of the clinker. Packaging and storage. You'll know all the process below in details. Treatment of raw materials. The raw materials, limestone and clay, are subjected to such processes as crushing, drying, grinding, proportioning, and blending or mixing before they are fed to the kilns for calcination or burning process. The crushing stage involves breaking the raw materials into small fragments that vary in size between 6 to 14 mm. Machines called crushers are used for this purpose. The drying stage is typical of the dry process. Drying of crushed materials is essential and is achieved by heating these materials, separately, at temperatures sufficiently high to drive out uncombined water. Heating is done in drying kilns which are generally of the rotary type. The grinding of each material as obtained from the dryers is done in two stages. First, the preliminary grinding, in which the materials are reduced to a fineness of 50 mesh. Ball mills are generally used for preliminary grinding. Second, the fine grinding, in which the size of the materials is reduced to 200 mesh. This is done by grinding in tube mills. Each raw material is thus reduced to a required degree of fineness and is stored separately in suitable storage tanks called silos or bins where from it can be drawn out conveniently in requisite quantities. Proportioning and blending. Predetermined proportions of finely dried and ground raw materials are mixed together before they are fed into the kiln. The different materials thus combined together are mixed very thoroughly either by mechanical or by pneumatic methods. In the pneumatic blending, materials from different storage silos are simultaneously drawn off and fed into a single silo that now contains mixed material. In the pneumatic method, dry, proportioned materials are pumped under passive into a blending silo, wherefrom they are drawn in the mixed state. The blended materials are now ready for feeding into the burning kilns. From this stage onwards, there is practically no major difference between the dry and wet processes, except in the design of the rotary kiln. Burning or calcination of the dry mix. The well-proportioned finely powdered mixture is charged into a long steel cylinder, called the rotary kiln. The kiln is adjusted in an inclined position, making an angle of 15 degrees with the horizontal and rotates around its longer axis, hence the name suggests. It has a charge end and a burner end, the former for introducing the materials, called feed, and the latter for supplying fuel. Rotary kilns differ in design and dimensions in accordance with the production requirements. Thus, these may be 100 to 180 meter in length, 3 to 5 meter in diameter and have a rotation of 60 to 90 revolutions per hour. Coal in finely pulverized form, fuel oil, and gas are common fuels used in these kilns. The raw mixture is burnt in the kiln until the proper burning is achieved. This is indicated by its taking a greenish black color and vitreous, shining like glass, luster. This burnt material, now called clinker, it is cement in composition but not in size, it is in about walnut-sized lumps when it comes out of the kiln. At least following 3 reactions are believed to take place in the charge during the burning stage. Complete dehydration. Dissociation of carbonates. Compound formation. A. Complete dehydration. Water is completely driven off at the very initial stages of burning at temperatures as low as 400 degrees Celsius. B. Dissociation of carbonates. Carbonates of calcium and magnesium are completely dissociated at temperatures between 800 to 900 degrees Celsius, as per following reactions. CaCO 3 equals CaO plus Co 2 MgCO 3 equals MgO plus Co 2 C. Compound formation. Lime and magnesia as formed above are combined in the next stage with silica, alumina, and ferric oxide to form the basic compounds of cement, namely, the tricalcium and dicalcium silicates, tricalcium aluminates and tetracalcium alumininoferrite. These compound formation reactions start at temperatures around 1200 degrees Celsius and require temperatures as high as 1550 degrees for their completion. It is, therefore, natural that they take place near the burner end of the rotary kiln. Alkalis, moisture, and other harmful gases, etc. are all expelled as waste gases during the burning of the raw materials in the kiln. Grinding of clinker. The completely burnt or calcined raw materials of cement are converted to a lump-shaped product called clinker, which is drawn out from the lower end of the rotary kiln. It is extremely hot when discharged, and is, therefore, first cooled in clinker coolers. A predetermined batch of gypsum, CaSO42H2O, is added to the cooled clinker, and both, clinker and gypsum, are sent for pulverizing. The mixture is reduced to an extremely fine powder by grinding it in 2 stages, the preliminary grinding and the fine grinding. The preliminary grinding is achieved by using a gyratory type of crushers, whereas for fine grinding use is made of tube mills. The tube mill crushers are generally provided with air separators through which material of desired fineness can only pass. The coarser portion of the cement is fed back into the mill for further grinding. Packing and storage of cement. This also forms a very important operational step, since cement needs very careful packing and storage arrangements. It is, in fact, a delicate product, and when handled carelessly can deteriorate to a useless set material. Cement is most commonly stored after its manufacture in specially designed concrete storage tanks called silos, where from it is drawn off mechanically for the market. For cement packing, cloth, jute, and high-density polythene, HDPE, bags are commonly used. For convenience, the cement comes to the customer in bags containing measured quantity. The standard bag of cement as distributed in India is commonly 50 kg or 112.5 lbs. Wet process of manufacturing of cement. The raw materials used for cement manufacturing are calcareous materials, such as limestone or chalk, and argillaceous materials such as shale or clay. Cement factories are installed where this raw material available in abundant quantity. Cement manufacturing units are placed near the consumption are, eliminating the inconvenience of long-distance transportation of raw and finished materials. The manufacturing process of cement consists of raw materials grinding, mixing this material in certain proportions depending upon their purity, and preparing composition. Burning this composition in a kiln at a temperature of about 1300 to 1500 degrees Celsius. The process out clinker is cooled and ground to a fine powder with the addition of about 3 to 5% of gypsum. The material produced by this process known as Portland cement. Figure showing wet process of manufacturing. The raw limestone from quarries is first crushed to small size fragments. Then it is mixed with clay or shale in ball or tube mill and ground to form a slurry of a fine consistency with the addition of water. The slurry is prepared with a water content of about 35 to 50%. Fine crushed particle are held in suspension. This slurry is taken to slurry tanks or basins by pumping, where it is kept in an agitated condition using rotating arms with chains. Also, blowing continuously compressed air from the bottom to prevent settling of limestone and clay particles. Slurry composition in the tank is tested to give the required chemical composition and corrected periodically in the tube mill. After that, the slurry is stored in the final storage tanks, and to keep slurry in homogeneous condition continuous the agitation is done in tank. This homogeneous slurry is sprayed onto the upper end of a rotary kiln against hot heavy hanging chains. Note: the rotary kiln is an essential and important component of a cement manufacturing factory. It is made of a thick steel cylinder of diameter anything from 3 meters to 8 meters, lined with refractory materials, mounted on roller bearings and capable of rotating about its axis at a specified speed. It may of any length from 30 meters to 200 meters. When the slurry is sprayed on the hot surface of the flexible chain, loses moisture and becomes flakes. These flakes, fragments, cut out and fall on the floor. The rotary kiln keeps rotating, causes the flakes to move from the upper end towards the lower end of the kiln. The rotary kiln is fired from the bottom end. The fuel is powered coal, oil, or natural gas. With time, the material accumulated to the lower end of the rotary kiln, the dry material undergoes a series of chemical reactions, in the hottest part of the kiln. At this point, the temperature is highest in the order of 1500 degree. About 20 to 30% of the materials get fused. At this stage, lime, silica, and alumina get recombined. The fused material turns into anodular form of size 3 mm to 20 mm known as clinker. This nodular form clinker collected into a rotary cooler where it is cooled under controlled conditions. The clinker is stored in silos or bins. These clinkers have weights about 1,100 to 1,300 gms per liter. The weight of the particle indicates the quality of clinker. These cooled clinkers are then taken in a ball mill with the addition of 3 to 5% of gypsum to prevent flash setting of the cement. For crushing the clinker, a ball mill is used. It consists of numbers of compartments charged with progressively smaller hardened steel balls. The particles are crushed to require fineness, are separated by currents of air and taken to storage silos from where the cement is bagged or filled into barrels. In the modern method of cement grading, the particle size distribution of cement particles is maintained in such a way as to give a desirable grading pattern. Same as the good grading of aggregates is essential for making good concrete, it is now recognized that good grading pattern of the cement particles is also important. Advantages: raw material can be mixed easily, so a better homogeneous material can be obtained. Capital cost, cost of establishment, is comparatively less. Disadvantages: mixing of raw materials in wash mill with 35 to 50% water. Materials exiting the mill are called slurry and have flowability characteristics. Size of the kiln needed for the manufacturing of cement is bigger. Fuel consumption is high, i.e., 350 kilograms of coal per ton of cement produced. Cost of production is high. How to check cement quality on construction site. Cement quality check, also called field tests on cement, are carried to know the quality of cement supplied at site. This check provides idea cement quality based on color, touch, and feels and other tests. Open the bag and take a good look at the cement. There should not be any visible lumps. The color of the cement should normally be greenish-gray. Thrust your hand into the cement bag. It must give you a cool feeling. There should not be any lump inside. Take a pinch of cement and feel between the fingers. It should give a smooth and not a gritty feeling. Take a handful of cement and throw it on a bucket full of water. The particles should float for some time before they sink. Below these are discussed in details. Points to be checked on a cement bag. On cement bag, you have to check the manufacturer's name and its registered trademark. If name and trademark are not properly printed or there is any spelling mistake, then the cement bag may be duplicated. We must check the ISI mark printed in black color on the cement bags. The ISI mark ensures about quality of cement that meet the requirements as per Indian standard, or the cement packed in the bag has fulfilled every requirement of the specifications. We must check grade and type of cement printed on a cement bag. On cement bag front side there should be mentioned OPC 53 in words also. For example, ordinary Portland cement, 53 grade, or ordinary Portland cement, 53S grade, whichever is applicable. Specified brand name of cement bag. It is important to check cement is of a reputable brand. We must also verify the delivery sheet provided by the brand, to know the technical details about the product. MRP, maximum retails price, check is also important check on a cement bag. The supplier or manufacturer can fool us by selling the cement bag for price more than MRP. Therefore, verifying the MRP before buying the cement bag will help the consumer to avoid any kinds of frauds. On standard brand of cement, there is printed use no hooks or symbol on cement bag. Check there should be batch control unit number in terms of the week, month and year of packing must be printed on the cement bag. It is secure to use a cement bag which is recently packed, usually less than 3 months. Check if the type and percentage of performance improver added, and if added must be printed on the cement bag. Reference IS code number should be printed on the cement bag. For example, if you have ordered OPC 53 grade cement, then IS 12269 1987 should be printed on the cement bag, and if you have ordered Portland Pozzolana cement, PPC, IS 1489 to 1991, should be printed on the cement bags. The above mentioned points are essential to check on a cement bag before buying it. This information will help you to ensure the cement bags are from a standard manufacturer. Field tests. Cement test on construction site. The following are the field quality tests on cement at the construction site. Color test. Presence of lumps. Adulteration test. Temperature test. Flow tests. Strength test. Setting test. Date of packing. Color test of cement. The cement should be uniform throughout within bag. It should be gray or light greenish shade. Presence of lumps. Cement smoothness test. The cement should give smooth feeling when touched or rubbed in between fingers, and if it is felt rough, it indicates adulteration with sand. The cement must be free from small lumps. Such lumps are formed due to absorption of moisture from the atmosphere. If any bag found to have such type of lumps should be rejected. Cement temperature test. As you immerse hand in cement, it should feel cool and not warm. Flow test. In flow test, a small amount of cement is thrown in the water, the particles should float for some time before it sinks. Setting test. In this test, cement is mixed with water and made a paste on a piece of the glass plate. This thick paste kept under water for 24 hours. It should set and not crack. Strength of cement test. Cement block of size 25 mm times 25 mm and 200 mm long is prepared and it is immersed for 7 days in water. After that, it is placed on supports 15 cm apart and it is loaded with a weight of about 34 kg. The cement block should not show signs of failure. Date of packing. We know that strength of cement reduces with time, so it is important to check the manufacturing date of the cement. Normally the cement should be used before 90 days from the date of manufacturing. Lab tests. Fineness test of cement procedure and importance. The fineness test of cement is done by sieving cement sample through standard IS sieve. The weight cement particle whose size greater than 90 microns is determined and the percentage of retained cement particle are calculated. This is known as fineness of cement. Why cement fineness test required? We know that cement hydrates when cement is mixed with the water and a thin layer are formed around the particle. This thin layer grows bigger and makes cement particles to separate. Because of this, the cement hydration process slows down. On other hands, cement's smaller particle react much quicker than the larger particle. A cement particle with diameter 1 μm will react entirely in 1 day, whereas the particle with diameter 10 μm takes about 1 month. But, there is a side effect of having too much of smaller particles in cement results in quick setting, leaving no time for mixing, handling and placing. Therefore, to increase the setting time of cement, cement must be manufactured in a different range of particle sizes. Test method. Aim. To determine the fineness of cement by using 90 μm IS sieve as per IS 4031, Part 1. 1996. 90 μm IS sieve. Weight balance having capacity 10 mg to 100 g. Nylon or pure bristle brush. Apparatus. Procedure. Collect a sample of cement and rub with your hands. The fineness test sample should be free of lumps. Take 100 gm of cement sample and note its weight as W1. Drop 100 gm of cement in 90 μm sieve and close it with the lid. Now, shake the sieve with your hands by agitating the sieve in planetary and linear movements for 15 minutes. After that, weight the retained cement on the 90 μm sieve as W2. Fineness equals W2/W1, asterisk 100. Then after, calculate the percentage of weight of cement retained on sieve. Repeat this procedure with 3 different samples of cement and average the values for accurate results. Result: the standard cement should have fineness less than 10% as per IS recommendations. Sister No. Weight of cement sample. Weight cement sample retained on 90 μm sieve. Fineness of cement. 1. 100 gm. 4.65. 4.65%. 2. 100 gm. 8.25. 8.25%. 3. 100 gm. 7.95. 7.95%. Average 6.95%. Soundness of cement. Soundness of cement is the ability of a hardened paste to retain its volume after setting. A cement is said to be unsound, i.e., having lack of soundness, if it is subjected to delayed destructive expansion. Unsoundness of cement is due to presence of excessive amount of hard burned free lime or magnesia. Soundness of cement indicates quality to expand on the setting. Unsound cement expands too much on setting and develops cracks in the structure. The test used for determining soundness of cement is known as Le Chatelier apparatus test. By soundness of cement, it is understood that its capacity to form a non-disintegrating, hard uniformly strong mass on the setting. This depends on its original composition, proper burning, and grinding. Presence of lime in the free state, an excess of sulfate or magnesia and a very fine size may be the cause of soundness in cement. The Indian Bureau of Standards has specified the Le Chatelier apparatus test. The same as adopted by British and American standards for soundness test of cement. Le Chatelier apparatus test. Apparatus. It consists of a small, split, metallic cylinder having an internal diameter of 30 mm. It is 30 mm in height, with the thickness of wall being 0.5 mm. It is fixed with 2 indicators, one fixed on either side of the split. The distance from the end of the indicator to the center of the cylinder is 165 mm. Other apparatus used in the Le Chatelier apparatus test are balance, measuring box, water bath, caliper. Le Chatelier apparatus. Glass sheets, enamel tray, trowel. Procedure. Before commencing setting time test, do the consistency test to obtain the water required to give the paste normal consistency, P. Prepare a paste by adding 0.78 times the water required to give a paste of standard consistency, i.e. 0.78 p. Lightly oil the Le Chatelier mold and place it on a lightly oiled glass sheet. The paste, of the known consistency, is filled in the cylindrical mold, covered with glass sheet and kept under water, at 27 degrees to 32 degrees centigrade, for 24 hours. After which the cylinder is taken out, and the distance between the two indicators is measured, say it is x. It is again immersed in the water. The water is then brought to the boiling point in 15 to 30 minutes and kept boiling for 1 hour, after which the distance between the two indicators is again measured, say it is now y. The difference of y gives the expansion of the cement specimen on the setting. It is specified that this distance shall not exceed 10 mm for the cement to qualify as soundness cement. Precautions. A good care should be taken while taking the measurements. Do not apply more pressure on the mold while filling it. The water level should not fall below the height of the mold during boiling. The expansion as determined by the above apparatus should not exceed 10 mm. Important points. In cement mortar and cement concrete, the volume expands due to the unburnt lime, CaO, and magnesia, MgO. Le Chatelier apparatus test is used to determine the presence of unburnt lime. CaO. The cracks developed in the structure are mostly due to the unburnt lime because it increases the volume of the cement. Lime and magnesia also react with water and thus increase in volume occur in the cement. Which is also areasin for cracks in the structures. Compressive strength test. Compressive strength is the basic data required for mix design. By this test, the quality and the quantity of concrete can be controlled and the degree of adulteration can be checked. Test procedure. The test specimens are 70.6 mm cubes having face area of about 5,000 square millimeter. Large size specimen cubes cannot be made since cement shrinks and cracks may develop. The temperature of water and test room should be 27 degrees plus or minus 2 degrees Celsius. A mixture of cement and standard sand in the proportion 1:3 by weight is mixed dry with a trowel for 1 minute and then with water until the mixture is of uniform color. 3 specimen cubes are prepared. The material for each cube is mixed separately. The quantities of cement, standard sand, and water are 185 g, 555 g and p/4 plus 3.5, respectively, where P equals percentage of water required to produce a paste of standard consistency. The mold is filled completely with the cement paste and is placed on the vibration table. Vibrations are imparted for about 2 minutes at a speed of 12,000 plus or minus 400 per minute. The cubes are then removed from the molds and submerged in clean fresh water and are taken out just prior to testing in a compression testing machine. Compressive strength is taken to be the average of the results of the 3 cubes. The load is applied starting from 0 at a rate of 35 N/square mm/minute. The compressive strength is calculated from the crushing load divided by the average area over which the load is applied. The result is expressed in N/mm². Tensile strength test. The tensile strength may be determined by briquette test method or by split tensile strength test. Importance. The tensile strength of cement affords quicker indications of defects in the cement than any other test. Also, the test is more conveniently made than the compressive strength test. Moreover, since the flexural strength is directly related to the tensile strength, this test is ideally fitted to give information both with regard to tensile and compressive strengths when the supply for material testing is small. Briquette test method. A mixture of cement and sand is gauged in the proportion of 1:3 by weight. The percentage of water to be used is calculated from the formula, P/5, plus 2.5, where P equals percentage of water required to produce a paste of standard consistency. The temperature of the water and the test room should be 27 degrees plus or minus 2 degrees C. The mix is filled in the molds of the shape. After filling the mold, an additional heap of mix is placed on the mold and is pushed down with the standard spatula, until the mixture is level with the top of the mold. This operation is repeated on the other side of the mold also. The briquettes in the mold are finished by smoothing the surface with the blade of a trowel. They are then kept for 24 hours at a temperature of 27 degrees plus or minus 2 degrees and in an atmosphere having 90% humidity. The briquettes are then kept in clean fresh water and are taken out before testing. 6 briquettes are tested and the average tensile strength is calculated. Load is applied steadily and uniformly, starting from 0 and increasing at the rate of 0.7 N/square mm of section in 12 seconds. Initial and final setting time. When water is added to cement, the resulting paste starts to stiffen and gain strength and lose the consistency simultaneously. The term setting implies solidification of the plastic cement paste. Initial and final setting times may be regarded as the two stiffening states of the cement. The beginning of solidification, called the initial set, marks the point in time when the paste has become unworkable. The time taken to solidify completely marks the final set, which should not be too long in order to resume construction activity within a reasonable time after the placement of concrete. The initial setting time may be defined as the time taken by the paste to stiffen to such an extent that the Vicat's needle is not permitted to move down through the paste to within 5 plus or minus 0.5 mm measured from the bottom of the mold. The final setting time is the time after which the paste becomes so hard that the angular attachment to the needle, under standard weight, fails to leave any mark on the hardened concrete. Initial and final setting times are the rheological properties of cement. Test procedure. A neat cement paste is prepared by gauging cement with 0.85 times the water required to give a paste of standard consistency. The stopwatch is started at the instant water is added to the cement. The mold resting on a non-porous plate is filled completely with cement paste and the surface of filled paste is leveled smooth with the top of the mold. The test is conducted at room temperature of 27 plus or minus 2 degrees C. The mold with the cement paste is placed in the Vicats apparatus and the needle is lowered gently in contact with the test block and is then quickly released. The needle thus penetrates the test block and the reading on the Vicats apparatus graduated scale is recorded. The procedure is repeated until the needle fails to pierce the block by about 5 mm measured from the bottom of the mold. The stopwatch is pushed off and the time is recorded, which gives the initial setting time. The cement is considered to be finally set when, upon applying the needle gently to the surface of test block, the needle makes an impression, but the attachment fails to do so. Grades of cement. Different grades of cement are specified by IS 1489-1991. Cements are mainly classified on the basis of compressive strength of particular cement. For example, if cement has compressive strength of 33 N/mm2, then it is classified under grade 33. Mainly 3 grades of cements are used. Grade 33 Ordinary Portland Cement. Grade 43 Ordinary Portland Cement. Grade 53 Ordinary Portland Cement. Grade 33 Ordinary Portland Cement. Fineness equals 300 m2/kg. Compressive strength after 3 days equals 16 N/mm2. Compressive strength after 7 days equals 22 N/mm2. Compressive strength after 28 days equals 33 N/mm2. Grade 33 cement has high workability and is mainly used for mortar in masonry work and for plastering. IS 269, 1989, covers the specification of grade 33 Ordinary Portland Cement. Grade 43 Ordinary Portland Cement. Fineness equals 225 m2/kg. Compressive strength after 3 days equals 23 N/mm2. Compressive strength after 7 days equals 33 N/mm2. Compressive strength after 28 days equals 43 N/mm2. Grade 43 cement is moderately sulfate resisting and has good workability. Grade 43 cement has low chloride content and thus resists corrosion on RCC. Grade 43 cement has smooth and better finish. Grade 43 cement is mainly used in ready-mix concrete, R.M.C. Reinforced cement concrete work, R.C.C. Precast concrete. Example in Delhi Metro pillars. Silos and chimneys. IS 8112, 1989, covers the specification of grade 43 ordinary Portland cement. Grade 53 ordinary Portland cement. Fineness equals 225 m2/kg. Compressive strength after 3 days equals 27 N/mm2. Compressive strength after 7 days equals 37 N/mm2. Compressive strength after 28 days equals 53 N/mm2. Grade 53 cement has low chloride content and is moderately sulfate resisting. Volume of cement required is less due to high strength and surface area, which saves the cost of construction. Grade 53 cement is used in industrial buildings, roads, and subways. Precast concrete. RCC bridges. Concrete sleeper for railways. IS 12269, 1987, covers the specification of grade 53 ordinary Portland cement. Different types of cement. Ordinary Portland cement, OPC. Portland Pozzolana cement, PPC. Rapid hardening cement. Quick setting cement. Low heat cement. Sulfate resisting cement. Portland slag cement, PSC. High alumina cement. White cement. Colored cement. Air entraining cement. Hydrophobic cement. Masonry cement. Expansive cement. Oil well cement. Ordinary Portland cement, OPC. This is the most common type of cement which is extensively used. It has good resistance to cracking and dry shrinkage but less resistance to chemical attack. OPC is not suitable for the construction work which is exposed to sulfates in the soil. Ordinary Portland cement is available in following types: 33 grade, 43 grade and 53 grade. The grade represents the strength of cement at 28 days. 33 grade equals 33 N/mm2. The composition of ordinary Portland cement. Argillaceous or silicates of alumina, clay and shale. Calcareous or calcium carbonate, limestone, chalk, and marl. Uses of ordinary Portland cement. It is used for general construction purposes. It is also used in most of the masonry works. Portland Pozzolana cement, PPC. Pozzolans are natural or synthetic materials that contain silica in reactive forms. It reacts with calcium hydroxide generated by hydrating cement to form additional cementations materials when it is finely divided. The composition of Portland Pozzolana cement. OPC clinker. Gypsum. Pozzolanic materials, fly ash, volcanic ash, and calcined clay or silica fumes. Uses of Portland pozzolana cement. PPC is usually used in hydraulic structures, marine structures, construction near the seashore, dam construction, etc. It is also used in pre-stressed and post-tensioned concrete members. As it gives a better surface finish, it is used in decorative and art structures. It is also used in the manufacture of precast sewage pipes. Difference between OPC and PPC. Sources: OPC, PPC. 1 Definition/components. A mixture of limestone and other raw materials like argillaceous, calcareous, gypsum is prepared and then grinded to prepare OPC. PPC is prepared by adding pozzolanic materials to OPC. So, the main components are OPC clinker, gypsum, and pozzolanic materials, 15-35%, which includes calcined clay, volcanic ash, fly ash, or silica fumes. 2. Strength. Initial strength is higher than PPC. PPC has higher strength than OPC over a longer period of time. 3. Heat of hydration. Generates more heat than PPC in hydration reaction, which makes it less suitable for mass casting. It has a slow hydration process and thus generates less heat than OPC. 4. Durability. Less durable in aggressive weather. More durable in aggressive weather. 5. Cost. Costlier than PPC. Cheaper than OPC. Difference between OPC and PPC. Sources: OPC, PPC. 7. Applications/uses. IDA suitable where fast construction is required but not suitable for mass concreting due to heat issue as mentioned above. It is suitable for all types of construction work. For example, RCC casting of buildings, mass concreting for bridges, and even plastering and other non-structural works. 8. Setting time. Lower than PPC. Its initial setting time is 30 minutes and final setting time is 280 minutes. Its faster setting time helps faster construction. Setting time of PPC is higher than OPC. Its initial setting time is 30 minutes and final setting time is 600 minutes. Its slower setting time helps to get better finishing. Difference between OPC and PPC. Sources: OPC, PPC. 9. Fineness. OPC has finiteness of 225 square mkg. It has lower fineness than PPC. So, it has higher permeability resulting lower durability. OPC has finiteness of 300 square mkg. It has higher fineness than OPC. So, it has lower permeability resulting in higher durability. 10 grades available. 33 grade, 43 grade, and 53 grade OPC cement are available. No specified grade of PPC cement is available. 11. Workability lower than PPC. Higher than OPC. 12. Resistance against chemical attack. It has lower resistance against alkalis, sulfates, chlorides etc. It has higher resistance against alkalis, sulfates, chlorides etc. Rapid hardening cement. Rapid hardening cement is very similar to ordinary Portland cement, OPC. The early strength is achieved by adding excessive C. 3. In the mix and by lowering the C. 2. Content in the cement. As the name itself resembling that, this type of cement is used where there is a need for high early strength. Example pavements, busiest roadways. The strength of rapid hardening cement at age of 3 days is almost same as the 7 days strength of ordinary Portland cement. It requires same water cement ratio as OPC. This type of cement is not used for massive concrete constructions. When finely grounded tricalcium silicate, C3S, is present in OPC with higher content, it gains strength more quickly than OPC. This type of OPC is called rapid hardening cement. Its initial setting time 30 minutes and final setting time 600 minutes. Uses of rapid hardening cement. Rapid hardening cement is mostly used where rapid construction is needed, like the construction of pavement. It also gives high strength. Quick setting cement. Quick setting cement is the cement which sets in a very short time. The initial setting time is 5 minutes and the final setting time is 30 minutes. The composition of quick setting cement. Clinker. Aluminium sulfate, 1% to 3% by weight of clinker. The aluminium salt increase the hydration rate of silicate. Uses of quick setting cement. It is used in underwater construction. It is also used in rainy and cold weather conditions. It is used at a higher temperature where water evaporates easily. Used for anchoring or rock bolt mining and tunneling. Low heat Portland cement. This type of cement is manufactured by lowering the C. 3. Content and increasing the C. 2. Content. It possesses less compressive strength than ordinary Portland cement. It has less lime content than OPC. This type of cement is mostly used in the construction of retaining walls, and it is strictly not suitable for thin concrete structures. It is a spatial type of cement which produce low heat of hydration during setting. Some chemical composition of ordinary Portland cement is modified to reduce the heat of hydration. The chemical composition of low-heat cement. A low percentage, 5%, of tricalcium aluminate, C3A. A higher percentage, 46%, of declaimed silicate, C2S. Uses of low-heat cement. It is used for the construction of dams, large footing, large raft slabs, and wind turbine plinths. It is also used for the construction of chemical plants. Sulfate-resisting Portland cement. It is manufactured by keeping the percentage of C3A below 5%. This type of cement is used where the structure is prone to severe sulfate attacks, alkaline conditions, such as construction in the foundation of soil, marine conditions, sewage treatment tanks. Sulfate-resisting cement is used to resist sulfates attacks in concrete. Due to the lower percentage of tricalcium aluminate, the production of calcium sulfoaluminates gets reduced. Uses of sulfates-resisting cement. Construction in contact with soils or groundwater having more than 0.2% or 0.3% Gl sulfate salts respectively. Concrete surfaces subjected to alternate wetting and drying such as bridge piers, concrete surface in tidal zone, apron, building near seacoast. Effluent treatment plants, chimney, chemical industries, water storage, sumps, drainage works, cooling towers, coastal protective works such as sea walls, breakwaters, tetrapods etc. High alumina cement. This type of cement has rich alumina content about 35%, which helps in gaining ultimate high strength within a short period. This type of cement is used where a structure is subjected to the action of seawater, chemical plants, and furnaces. High alumina cement is obtained by mixing calcining bauxite, it's an aluminium ore, and ordinary lime with clinker during the manufacture of OPC, in which the total amount of alumina content should not be lesser than 32% and it should maintain the ratio by weight of alumina to the lime between 0.85 to 1.30. Uses of high alumina cement. It is used where concrete structures are subjected to high temperatures like workshop, refractory, foundries etc. It also used where the concrete is subjected to frost and acidic action. Portland slag cement, PSC. Portland slag cement, commonly known as PSC, is blended cement. Slag is, essentially, a non-metallic product comprising of more than 90% glass with silicates and aluminosilicates of lime. It is created with a combination of up to 45-50% slag, 45% 50% clinker, and 3-5% gypsum. Portland Pozzolana cement, also known as PPC, on the other hand, is created of pozzolans, which are siliceous material that can be added to concrete mixtures, potentially lower the mix cost without harming the performance characteristics. White cement. White cement is quite similar to ordinary Portland cement except for color. Amounts of iron oxide and manganese oxide are low in white cement. It is expensive than OPC, so not economical for ordinary work. This type of cement is obtained by lowering the iron oxide content in the ordinary Portland cement. The strength and durability is same as OPC. This type of cement is used for joining tiles and other interior works. Uses of white cement. It is usually used in decorative work. It can also use for traffic barriers, tile grouts, swimming pools, roof tiles, patching materials and terrazzo surfaces. Colored cement. This type of cement is also known as Calcrete. It is manufactured by adding coloring pigment to the OPC. It is used in joining tiles. To make 5 to 10% of suitable pigments are grinded with OPC. Types of pigments are selected according to the desired color. Uses of colored cement. Colored cement is used for different decorative work. Air entraining cement. This type of cement is manufactured by adding 0.025-0.1% of air entraining agents to the ordinary Portland cement clinker. Air entraining agents are generally made up of wood resins, calcium agents, vegetable oils, and animal fats. It is seen that entrainment of air or formation of gas bubbles while applying cement increases resistance to frost action, fire, scaling and other similar defects. Air entraining cement is a special type of cement which entrains tiny air bubbles in concrete. It is produced by grinding minute air entraining materials with clinker by adding some resinous materials, e.g. Vinsol resin, to ordinary Portland cement. When the water in concrete gets frizzed due to low temperature, it expands. When air entraining cement, the air voids in concrete provide space for water to expand without cracking concrete. But this type of cement does not provide high strength in concrete. Uses of air entraining cement. Especially it is used in areas where the temperature is very low. It also resists sulfate attack. It is used where the de-icing chemical is used. Hydrophobic cement. This type of cement is manufactured by grinding ordinary Portland cement clinker with water, oleic acid or stearic acid. These acids forms as a water-repellent film around the cement particle, which increases the shelf life of cement. The formed around each grain of cement reduces the rate of deterioration of the cement during long storage, transport, or under unfavorable conditions. The film is broken out when the cement and aggregate are mixed together at the mixer, exposing the cement particles for normal hydration. To resist the hydration process in the transportation or storage stage, clinkers are grinded with water-repellent film substance such as oleic acid or stearic acid. These chemicals form a layer on the cement particle and do not allow water to mix and start the hydration process. When cement and aggregate are thoroughly mixed in the mixer, protective layers break and start normal hydration with some air entrainment, which increases workability. Uses of hydrophobic cement. Usually, it is used in the construction of water structures such as dams, spillways, or other submerged structures. It is also used in the construction of underground structures like tunnel, etc. Expansive cement. This type of cement is manufactured by adding stabilizer, which stabilizes the cement to expand. This can be achieved by adding 8–20% of sulfoaluminate and 15% of stabilizer to the ordinary Portland cement clinker. Concrete made up of OPC shrinks while setting due to loss of free water. Concrete also shrinks continuously for a long time. Cement used for grouting should not shrink or change volume. For this, we use expansive cement. The expansive cement doesn't show any volume change after hardening. In the hydration process, the expansive cement expands its volume. It can be possible to overcome shrinkage loss by using expansive cement. There are three types of expansive cement. K-type expansive cement, M-type expansive cement, S-type expansive cement. K-type expansive cement. Raw materials of these types of cement: Portland cement, anhydrous tetracalcium trialuminate sulfate, C4A3S, calcium sulfate, CaSO4, lime, CaO. M-type expansive cement. Raw materials of these types of cement: Portland cement clinkers, calcium sulfate. S-type expansive cement. Raw materials of these types of cement: Portland cement clinkers, calcium sulfate, high amount. Tricalcium aluminate, C3A, high amount. Uses of expansive cement. It is used in the construction of the pre-stressed concrete component. It is also used for sealing joints and grouting anchor bolt. In the construction of different hydraulic structures, this type of cement is used. Waterproof Portland cement. This type of cement is manufactured by adding small percentages of metal cerates in OPC during grinding. This type of cement is used in foundations, water tanks and other water-retaining structures. Oil well cement. In order to extract oil from the stratified sedimentary rocks, oil wells are dug to a greater depth. For safe pumping out of extracted oil, steel casing is inserted. It is likely that if oil is struck, oil or gas may escape through the space between the rock formation and steel casing. To fill this space, oil well cement is used. Oil well cement is manufactured by adding retarders, starches or cellular products, to ordinary Portland cement. Hydration of Portland cement. Introduction. Portland cement is a hydraulic cement, hence it derives its strength from chemical reactions between the cement and water. The process is known as hydration. Cement consists of the following major compounds. See composition of cement. Tricalcium silicate, C3S. Dicalcium silicate, C2S. Tricalcium aluminate, C3A. Tetracalcium aluminoferrate, C4AF. Gypsum, CSH2. Chemical reactions during hydration. When water is added to cement, the following series of reactions occur. The tricalcium aluminate reacts with the gypsum in the presence of water to produce ettringite and heat. Tricalcium aluminate and gypsum and water rightward arrow ettringite plus heat C. 3. A plus 3 CSH. 2. Plus 2 6H rightward arrow C. 6. As 3. H. 32. H equals 207 Cal G. Ettringite consists of long crystals that are only stable in a solution with gypsum. The compound does not contribute to the strength of the cement glue. The tricalcium silicate, alite, is hydrated to produce calcium silicate hydrates, lime, and heat. Tricalcium silicate and water rightward arrow calcium silicate hydrate and lime and heat 2C. 3. S plus 6H rightward arrow C. 3. S. 2. H. 3. Plus 3CH. H equals 120 Cal G. The CSH has a short networked fiber structure which contributes greatly to the initial strength of the cement glue. Once all the gypsum is used up as per reaction, the ettringite becomes unstable and reacts with any remaining tricalcium aluminate to form monosulfate aluminate hydrate crystals. Tricalcium aluminate and ettringite and water rightward arrow monosulfate aluminate hydrate. 2C. 3. A plus 3C. 6. As 3. H 32 plus 2 2H rightward arrow 3C 4 Ash 18. The monosulfate crystals are only stable in a sulfate-deficient solution. In the presence of sulfates, the crystals resort back into ettringite, whose crystals are 2.5 times the size of the monosulfate. It is this increase in size that causes cracking when cement is subjected to sulfate attack. The belite, dicalcium silicate, also hydrates to form calcium silicate hydrates and heat. Dicalcium silicates and water rightward arrow calcium silicate hydrate and lime C. S plus 4H rightward arrow C. S. H. Plus CH, H equals 62 cal G. Like in reaction 2, the calcium silicate hydrates contribute to the strength of the cement paste. This reaction generates less heat and proceeds at a slower rate, meaning that the contribution of C 2 the strength of the cement paste will be slow initially. This compound is however responsible for the long-term strength of Portland cement concrete. The ferrite undergoes two progressive reactions with the gypsum. In the first of the reactions, the ettringite reacts with the gypsum and water to form ettringite lime and alumina hydroxides, i.e. ferrite and gypsum and water rightward arrow ettringite plus ferric aluminum hydroxide and lime C. 4. AF plus 3 CSH. 2. Plus 3H rightward arrow C. 6. AF, S. 3. H. 32. Plus, AF, H. 3. Plus CH. The ferrite further reacts with the ettringite formed above to produce garnets, i.e. ferrite and ettringite and lime and water rightward arrow garnets C. 4. AF and C. 6. AF, S. 3. H. 32. Plus 2CH plus 2 3H rightward arrow 3C4, AF, SH. 18. Plus, AF, H. 3. The garnets only take up space and do not in any way contribute to the strength of the cement paste. The hardened cement paste. Hardened paste consists of the following: ettringite 15 to 20%, calcium silicate hydrates, CSH 50 to 60%, calcium hydroxide, lime, 20 to 25%, voids 5 to 6%, in the form of capillary voids and entrapped and entrained air. Conclusion: it can therefore be seen that each of the compounds in cement has a role to play in the hydration process. Uses of cement. Some of the numerous functions of cement are given below. It is used in mortar for plastering, masonry work, pointing, etc. It is used for making joints for drains and pipes. It is used for water tightness of structure. It is used in concrete for laying floors, roofs and constructing lintels, beams, stairs, pillars, etc. It is used where a hard surface is required for the protection of exposed surfaces of structures against the destructive agents of the weather and certain organic or inorganic chemicals. It is used for precast pipes manufacturing, piles, fencing posts, etc. It is used in the construction of important engineering structures such as bridges, culverts, dams, tunnels, lighthouses, etc. It is used in the preparation of foundations, watertight floors, footpaths, etc. It is employed for the construction of wells, water tanks, tennis courts, lamp posts, telephone cabins, roads, etc.
Thank you for watching. Please subscribe to the channel and press the bell icon.